Hello there, and welcome to tonight's journey into the strange and beautiful world that exists beneath everything you can see. Tonight, we'll explore quantum mechanics, the science that describes reality at its smallest scale, a place where particles can be in two places at once, where observation changes reality itself, and where the very fabric of existence operates according to rules that seem to defy common sense. Let your breathing slow. Allow your mind to soften. The universe at its tiniest scale is about to reveal its secrets, one calm fact at a time. Quantum mechanics describes the behavior of matter and energy at the atomic and subatomic scale. It is the physics of the incredibly small governing everything from electrons orbiting atoms to photons of light traveling through space. At these microscopic dimensions, the rules that govern our everyday experience no longer apply. Objects behave in ways that would seem impossible in the world we can see and touch. A baseball follows a predictable path when thrown. An electron does not. Instead, it exists as a cloud of possibilities until the moment it is observed. This is the realm where science meets mystery, where mathematics describes phenomena that challenge our deepest intuitions about how reality works. The word quantum comes from the Latin term meaning how much. It refers to the discrete, indivisible units that make up the fabric of reality at the smallest scales. Energy, momentum, and other properties do not flow smoothly at the quantum level. Instead, they come in specific packets, like steps on a staircase rather than a smooth ramp. These packets are called quanta. A single packet is called a quantum. This idea revolutionized physics in the early 20th century, overturning centuries of assumptions about how nature operates. Before quantum mechanics, scientists believed that energy and matter were infinitely divisible. Quantum theory revealed that at the deepest level, reality is granular, made of fundamental units that cannot be subdivided further without changing their essential nature. Quantum mechanics emerged in the early 1900s when classical physics could not explain certain experimental results. Scientists observed phenomena that contradicted everything they thought they understood. Light behaved sometimes as a wave, sometimes as a particle. Atoms emitted light only at specific wavelengths, not across a continuous spectrum. Materials glowed in colors that depended on their temperature in ways classical theory could not predict. These mysteries demanded a new framework, a radical reimagining of how matter and energy actually behave. Between 1900 and 1930, physicists including Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger developed the theories that would become quantum mechanics. Their work remains one of the greatest intellectual achievements in human history. Max Planck solved the blackbody radiation problem in 1900 by proposing that energy is quantized. A blackbody is an idealized object that absorbs all radiation that falls upon it and emits radiation in a characteristic pattern depending on its temperature. Classical physics predicted that such objects would emit infinite energy at short wavelengths, an absurdity known as the ultraviolet catastrophe. Planck resolved this by suggesting that energy could only be emitted or absorbed in discrete packets, which he called quanta. The energy of each quantum is proportional to the frequency of the radiation, with the constant of proportionality now known as Planck's constant. This seemingly simple proposal marked the birth of quantum theory, though Planck himself initially viewed it as a mathematical trick rather than a description of physical reality. Albert Einstein extended quantum ideas in 1905 when he explained the photoelectric effect. Certain metals emit electrons when illuminated by light, but only if the light exceeds a particular frequency. Brighter light of insufficient frequency produces no electrons at all, while even dim light of high enough frequency causes emission. Classical wave theory could not explain this. Einstein proposed that light itself comes in discrete packets called photons, each carrying a specific amount of energy determined by its frequency. When a photon strikes an electron in the metal with enough energy, the electron is ejected. This work earned Einstein the Nobel Prize in Physics in 1921 and provided crucial evidence that light possesses particle properties in addition to its wave nature. Niels Bohr developed the first quantum model of the atom in 1913. Before Bohr, the structure of atoms was poorly understood. Scientists knew atoms contained negatively charged electrons and a positively charged nucleus, but classical physics predicted that orbiting electrons should spiral into the nucleus within fractions of a second, radiating energy continuously. This clearly did not happen. Bohr proposed that electrons occupy specific allowed orbits with fixed energies, and that they can only transition between these orbits by absorbing or emitting a quantum of energy. This explained why atoms emit light only at certain discrete wavelengths, producing the characteristic spectral lines observed in laboratory experiments. Bohr's model was a crucial stepping stone, though it would later be superseded by more complete quantum theories. The wave nature of matter was proposed by Louis de Broglie in 1924. If light, traditionally understood as a wave, could behave like a particle, perhaps particles, traditionally understood as discrete objects, could behave like waves. De Broglie suggested that every particle has an associated wavelength, inversely proportional to its momentum. For large objects like baseballs, this wavelength is unimaginably small and produces no observable effects. For electrons and other subatomic particles, the wavelength is significant and leads to measurable wave phenomena such as interference and diffraction. This hypothesis was soon confirmed experimentally when electrons were shown to produce interference patterns, just like light waves. De Broglie's work earned him the Nobel Prize in Physics in 1929 and established wave-particle duality as a fundamental principle of nature. Werner Heisenberg formulated matrix mechanics in 1925, providing the first complete mathematical framework for quantum mechanics. His approach focused on observable quantities like the energy levels and transition probabilities of atomic systems, deliberately avoiding attempts to visualize what was happening inside atoms. Heisenberg's theory used mathematical objects called matrices to represent physical observables. These matrices do not commute, meaning that the order in which you multiply them matters. This non-commutativity reflects a deep feature of quantum reality and leads directly to one of the most famous results in physics, the uncertainty principle. Heisenberg shared the Nobel Prize in Physics in 1932 for this groundbreaking work, which showed that classical concepts like definite trajectories of particles simply do not apply at the quantum level. Erwin Schrödinger developed wave mechanics in 1926, offering a different mathematical approach to quantum theory. He constructed a wave equation that describes how the quantum state of a physical system changes over time. The solutions to this equation are wave functions, mathematical objects that encode all the information about a quantum system. Schrödinger's approach was more intuitive to many physicists than Heisenberg's matrices because it used familiar mathematical techniques from wave theory. It soon became clear that Schrödinger's wave mechanics and Heisenberg's matrix mechanics were mathematically equivalent, two different formulations of the same underlying theory. Schrödinger was awarded the Nobel Prize in Physics in 1933. His equation remains the foundation of quantum mechanics, used today to describe everything from simple atoms to complex molecules and materials. Max Born introduced the probabilistic interpretation of the wave function in 1926. When Schrödinger first proposed his wave equation, it was unclear what the wave function actually represented physically. Born suggested that the wave function does not describe the physical location of a particle, but rather encodes the probability of finding the particle at different locations when a measurement is made. Specifically, the probability is proportional to the square of the wave function's magnitude. This interpretation means that quantum mechanics is fundamentally probabilistic. Even with complete knowledge of a quantum system, we can only predict the likelihood of different outcomes, not determine with certainty what will happen. This troubled some physicists, including Einstein, but Born's interpretation has been confirmed by countless experiments. Born received the Nobel Prize in Physics in 1954 for this crucial insight. The Heisenberg uncertainty principle states that certain pairs of properties cannot both be known with perfect precision simultaneously. The most famous example involves position and momentum. The more precisely you know where a particle is located, the less precisely you can know how fast it is moving, and vice versa. This is not a limitation of measurement technology, but a fundamental feature of nature itself. The product of the uncertainties in position and momentum must always be greater than or equal to a specific value related to Planck's constant. Similar uncertainty relations exist between energy and time, between angular momentum components, and between other pairs of complementary observables. The uncertainty principle reflects the wave nature of quantum particles and arises mathematically from the properties of wave functions. It sets absolute limits on what can be known and has profound implications for the nature of reality at the quantum scale. Wave-particle duality means that every quantum object exhibits both wave-like and particle-like properties. Light can create interference patterns like a wave, yet it also delivers energy in discrete packets like particles. Electrons can diffract through narrow slits like waves, yet they always arrive at detectors as localized particles. Neither description is complete on its own. The wave and particle aspects are complementary, revealing themselves in different experimental contexts. When you design an experiment to detect wave properties, you observe waves. When you design an experiment to detect particle properties, you observe particles. But you cannot observe both aspects simultaneously. This complementarity, articulated by Niels Bohr, suggests that our classical concepts of waves and particles are approximations that break down at the quantum level. The true nature of quantum objects transcends both descriptions. The double-slit experiment demonstrates the strange nature of quantum superposition. When you fire particles one at a time toward a barrier with two narrow slits, they pass through and hit a detection screen on the other side. Classical intuition suggests each particle goes through one slit or the other. But when you repeat the experiment many times, the particles accumulate in an interference pattern with alternating bright and dark bands, exactly as waves would. This implies that each particle somehow goes through both slits simultaneously, interfering with itself. Yet if you try to determine which slit the particle actually passes through by placing a detector there, the interference pattern vanishes. The particle then behaves as if it went through just one slit. The act of observation fundamentally changes the behavior of the system. This experiment has been performed with photons, electrons, atoms, and even large molecules, always with the same mysterious result. Quantum superposition means a particle can exist in multiple states at once until it is measured. An electron can be in a superposition of being in two different places. A photon can be in a superposition of having two different polarizations. The particle does not secretly have one definite state that we simply do not know. Rather, it genuinely possesses aspects of multiple states simultaneously. This is described mathematically by adding together the wave functions corresponding to each possible state. When a measurement is made, the superposition collapses to one definite outcome, with probabilities determined by the wave function. Superposition is not just a theoretical abstraction. It has been directly verified in countless experiments, and is the foundation for emerging quantum technologies like quantum computers, which exploit superposition to process vast amounts of information simultaneously. Quantum entanglement occurs when two or more particles become correlated in such a way that the quantum state of the system cannot be described independently for each particle. If you measure a property of one entangled particle, you instantly know the corresponding property of the other particle, no matter how far apart they are. Einstein called this spooky action at a distance because it seemed to imply faster than light communication. However, entanglement does not allow information to travel faster than light. It reflects a deep correlation in the properties of the entangled particles that was established when they interacted. Entangled states have no classical analog. They represent a fundamentally quantum phenomenon, where the whole system possesses properties that cannot be reduced to properties of individual parts. Entanglement has been experimentally verified over distances of hundreds of kilometers and forms the basis for quantum cryptography and quantum teleportation. The Einstein-Podolsky-Rosen paradox challenged the completeness of quantum mechanics. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a thought experiment designed to show that quantum mechanics could not be a complete description of reality. They considered two entangled particles separated by a large distance. According to quantum mechanics, measuring one particle instantly determines the state of the other, regardless of the separation. Einstein and his colleagues argued that this implied either faster-than-light influences, which violated relativity, or that the particles possessed definite properties all along, which quantum mechanics simply failed to describe. They believed this demonstrated that quantum mechanics was incomplete, and that hidden variables must exist to determine outcomes that quantum theory treats as probabilistic. John Bell devised a way to test whether hidden variable theories could reproduce quantum predictions. In 1964, he derived mathematical inequalities that any local hidden variable theory must satisfy. These Bell inequalities set limits on how strongly correlated measurements on entangled particles can be if the correlations arise from pre-existing properties rather than quantum entanglement. Quantum mechanics predicts that certain entangled states will violate Bell's inequalities, producing stronger correlations than any local hidden variable theory allows. This transformed the debate from philosophy into experimental physics, providing a concrete way to test the foundations of quantum mechanics. John Clauser and Stuart Friedman performed the first experimental test of Bell's inequality in 1972. Working at the University of California, Berkeley, they generated pairs of entangled photons using atomic transitions in calcium and measured their polarizations at different angles. Their results showed violations of Bell's inequality consistent with quantum mechanics and inconsistent with local hidden variable theories. The experiment had some loopholes that allowed for alternative explanations, but it was a groundbreaking first step in demonstrating that nature really does behave as quantum mechanics predicts. Alain Aspect conducted more sophisticated tests of Bell's inequality in the early 1980s. His experiments closed important loopholes present in earlier tests by switching the measurement settings while the photons were in flight, ensuring that the choice of what to measure could not be communicated between the particles even at the speed of light. Aspect's results confirmed violations of Bell's inequality with high statistical significance, providing strong evidence that local hidden variable theories cannot explain quantum correlations. The experiments were a triumph for quantum mechanics and demonstrated that entanglement is a real physical phenomenon. Anton Zeilinger extended Bell tests and pioneered quantum teleportation experiments. His work in the 1990s and 2000s demonstrated entanglement over increasingly large distances and closed additional experimental loopholes. In 1997, his group achieved the first quantum teleportation, transferring the quantum state of one photon to another using entanglement. Zeilinger's contributions to quantum information science have been profound, showing that quantum mechanics is not just a theory of microscopic particles, but a foundation for new technologies. Clauser, Aspect, and Zeilinger shared the Nobel Prize in Physics in 2022 for their experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Their work confirmed that quantum entanglement is real and that nature exhibits non-local correlations that cannot be explained by any local realist theory. These experiments resolved one of the longest-standing debates in physics and opened the door to practical applications of quantum mechanics in communication and computation. The Copenhagen interpretation is the most widely taught interpretation of quantum mechanics. Developed primarily by Niels Bohr and Werner Heisenberg in the 1920s, it states that the wave function provides a complete description of a quantum system. But this description is inherently probabilistic. Before measurement, particles do not have definite properties. Instead, they exist in superpositions described by wave functions. The act of measurement causes the wave function to collapse to one definite outcome. The Copenhagen interpretation emphasizes complementarity, the idea that different experimental setups reveal complementary aspects of quantum systems that cannot be observed simultaneously. It avoids metaphysical questions about what is really happening before measurement, focusing instead on what can be predicted about measurement outcomes. Many worlds' interpretation suggests that all possible outcomes of quantum measurements actually occur. Proposed by Hugh Everett in 1957, this interpretation eliminates wave function collapse. Instead, when a measurement occurs, the universe splits into multiple branches, one for each possible outcome. In one branch, you measure the electron's spin up. In another branch, you measure it spin down. Both outcomes are equally real, but observers in each branch perceive only the outcome in their own branch. The many worlds interpretation is deterministic and preserves the wave function's unitary evolution, but it requires accepting an enormous number of parallel universes. While it has gained adherence among some physicists, it remains controversial and philosophically challenging. Pilot wave theory, also called de Broglie-Bohm theory, is a deterministic interpretation of quantum mechanics. Proposed initially by Louis de Broglie in 1927 and later developed by David Bohm in 1952, it suggests that particles always have definite positions guided by a quantum wave. The wave evolves according to the Schrödinger equation, and the particle's trajectory is determined by the shape of this wave. Unlike the Copenhagen interpretation, pilot wave theory includes us hidden variables. The particle's precise position and velocity exist at all times, but these values are hidden from us because we cannot prepare quantum systems with sufficiently precise initial conditions. Pilot wave theory reproduces all the predictions of standard quantum mechanics, but offers a very different picture of what is actually happening. Quantum tunneling allows particles to pass through barriers they classically could not surmount. Imagine rolling a ball toward a hill. If the ball does not have enough energy to reach the top, it will roll back down. In quantum mechanics, there is a non-zero probability that the particle will appear on the other side of the barrier, as if it tunneled through. This happens because the wave function extends into and beyond the barrier, allowing a finite probability of finding the particle there. Tunneling is not just theoretical. It is responsible for radioactive alpha decay, where particles escape from atomic nuclei. It enables nuclear fusion in the Sun, where protons tunnel through the electrostatic repulsion barrier to fuse and release energy. Tunneling is exploited in technologies like the scanning tunneling microscope, which can image individual atoms. The scanning tunneling microscope uses quantum tunneling to create images with atomic resolution. A sharp metallic tip is brought extremely close to a conducting surface, typically within a nanometer. A voltage applied between the tip and surface causes electrons to tunnel through the gap. The tunneling current depends exponentially on the distance, so even tiny changes in the separation are detected. By scanning the tip across the surface and measuring the current, scientists construct three-dimensional maps showing individual atoms. Invented by Gerd Binnig and Heinrich Rohrer in 1981, the scanning tunneling microscope earned them the Nobel Prize in Physics in 1986 and revolutionized nanotechnology and surface science. Quantum computing exploits superposition and entanglement to perform certain calculations exponentially faster than classical computers. A classical computer bit is either 0 or 1. A quantum bit, or qubit, can be in a superposition of 0 and 1 simultaneously. With multiple qubits, you can represent many possible values at once. Quantum gates manipulate these superpositions, allowing a quantum computer to explore many potential solutions in parallel. When a measurement is made, the superposition collapses to one answer, hopefully the correct one. Algorithms like Shor's algorithm for factoring large numbers and Grover's algorithm for searching databases demonstrate quantum speedup. Building practical quantum computers is extraordinarily difficult because qubits are fragile and easily disturbed by their environment, causing errors. Nevertheless, companies and research labs worldwide are making steady progress, and small quantum computers already exist. Quantum cryptography uses the principles of quantum mechanics to enable provably secure communication. The most famous protocol, quantum key distribution, allows two parties to generate a shared secret key by transmitting qubits over a quantum channel. Any attempt to intercept and measure the qubits disturbs them in a detectable way, alerting the communicators to the presence of an eavesdropper. Security does not rely on computational difficulty, but on the fundamental laws of physics. Even with unlimited computing power, an eavesdropper cannot extract the key without being detected. Quantum key distribution has been demonstrated over fiber optic cables and through open air, including satellite-to-ground links. It represents one of the first practical applications of quantum information science. Quantum teleportation transfers the quantum state of one particle to another distant particle without physically moving the particle itself. Discovered theoretically in 1993, it relies on entanglement and classical communication. Suppose Alice has a particle whose state she wants to send to Bob. If Alice and Bob share an entangled pair of particles, Alice can perform a joint measurement on her particle and her half of the entangled pair. This measurement destroys the original state, but produces information that Alice sends to Bob classically. Bob uses this information to manipulate his half of the entangled pair, transforming it into an exact replica of Alice's original particle. No faster-than-light communication occurs because classical information must travel from Alice to Bob. Quantum teleportation has been demonstrated with photons, atoms, and ions over distances exceeding 1,000 kilometers using satellites. The Pauli exclusion principle states that no two identical fermions can occupy the same quantum state simultaneously. Fermions are particles with half-integer spin, such as electrons, protons, and neutrons. If you try to place two electrons in exactly the same quantum state, with the same position, momentum, and spin orientation, nature prevents it. This principle explains the structure of the periodic table. Electrons in atoms occupy discrete orbitals, and each orbital can hold at most two electrons with opposite spins. When lower orbitals are filled, additional electrons must occupy higher energy orbitals. This layering of electrons determines chemical properties. Without the exclusion principle, all electrons would collapse into the lowest energy state, and complex chemistry would be impossible. Wolfgang Pauli formulated this principle in 1925 and received the Nobel Prize in Physics in 1945. Quantum decoherence explains why we do not observe quantum superpositions in everyday objects. When a quantum system interacts with its environment, such as air molecules or thermal radiation, the environment effectively measures the system, causing the superposition to collapse into a definite state. This process happens extraordinarily quickly for macroscopic objects, which interact with countless environmental particles every instant. For microscopic systems isolated from their surroundings, decoherence can be minimized, allowing quantum behavior to persist. Decoherence reconciles the quantum and classical worlds, showing why quantum effects are prominent at small scales but invisible at large scales. It does not resolve all interpretational questions about quantum mechanics, but it explains the practical transition from quantum to classical behavior. Quantum field theory extends quantum mechanics to systems with an infinite number of degrees of freedom. In ordinary quantum mechanics, you deal with a fixed number of particles. Quantum field theory allows particles to be created and destroyed, accommodating the requirements of special relativity where energy and mass are interchangeable. Each type of particle is associated with a quantum field pervading all of space. Particles are quantized excitations of these fields. For example, photons are quanta of the electromagnetic field, and electrons are quanta of the electron field. Quantum field theory is the framework for the standard model of particle physics, which describes electromagnetic, weak, and strong nuclear forces. It has made predictions confirmed to extraordinary precision, making it one of the most successful theories in physics. Quantum electrodynamics is the quantum field theory of electromagnetism. Developed in the 1940s by Richard Feynman, Julian Schwinger, and Sin Itiro Tomonaga. It describes how light and matter interact. Electrons and photons are treated as excitations of their respective quantum fields, and their interactions are calculated using methods involving virtual particles and intricate diagrams called Feynman diagrams. Quantum electrodynamics predicts the magnetic moment of the electron to 1 part in a billion, one of the most accurate predictions in all of science. The 3 pioneers shared the Nobel Prize in Physics in 1965 for this monumental achievement. The standard model of particle physics is a quantum field theory describing 3 of the 4 fundamental forces. It unifies the electromagnetic, weak and strong nuclear forces into a single framework. Particles are classified into fermions, which make up matter, and bosons, which mediate forces. Quarks and leptons are the fundamental fermions. Photons, W and Z bosons, and gluons are the force carriers. The Higgs boson, discovered in 2012 at the Large Hadron Collider, gives mass to other particles through their interaction with the Higgs field. The standard model has been tested extensively and agrees with experiments to remarkable precision. However, it does not include gravity, does not explain dark matter or dark energy, and leaves many questions unanswered. Physicists continue searching for a more complete theory. Quantum chromodynamics is the theory of the strong nuclear force that holds quarks together inside protons and neutrons. Quarks carry a property called color charge, analogous to electric charge, but with 3 types instead of 2. Gluons mediate the strong force between quarks and themselves, carry color charge, leading to rich and complex behavior. Unlike electromagnetism, where charges can exist in isolation, quarks are confined inside composite particles called hadrons and cannot be separated. Quantum chromodynamics predicts that the force between quarks increases with distance, explaining why individual quarks have never been observed. The theory also accounts for jets of particles observed in high-energy collisions and the masses of protons and neutrons. The Higgs mechanism explains how particles acquire mass. In the standard model, particles would naturally be massless. The Higgs field, which fills all of space, interacts with particles as they move through it. This interaction endows them with mass, with the strength of the interaction determining how much mass a particle has. Photons do not interact with the Higgs field and remain massless. Electrons interact weakly and have small mass. W and Z bosons interact strongly and are heavy. The Higgs boson is a quantum of the Higgs field, and its discovery at CERN in 2012 confirmed the mechanism. François Englert and Peter Higgs received the Nobel Prize in Physics in 2013 for their theoretical predictions made in the 1960s. Zero-point energy is the lowest possible energy that a quantum system can have. Even at absolute zero temperature, when classical physics predicts all motion should cease, quantum systems retain some energy due to the uncertainty principle. A particle confined in a potential well cannot have zero momentum and zero position uncertainty simultaneously, so it must retain kinetic energy. This zero-point energy has measurable effects. It contributes to the stability of atoms, prevents helium from solidifying at atmospheric pressure, even at absolute zero, and gives rise to the Casimir effect, where two uncharged metal plates in a vacuum experience an attractive force due to quantum fluctuations. The Casimir effect demonstrates that the quantum vacuum is not empty. Hendrik Casimir predicted in 1948 that two uncharged parallel metal plates placed close together in a vacuum would attract each other. The plates restrict the types of virtual particles that can exist between them, while all modes are allowed outside. This creates a pressure difference, pushing the plates together. The effect has been measured experimentally and confirms quantum field theory predictions about vacuum fluctuations. It also has practical implications in nanotechnology, where Casimir forces can affect tiny mechanical devices. Virtual particles are temporary fluctuations allowed by the uncertainty principle. For very short times, energy conservation can be violated, allowing particle-antiparticle pairs to spontaneously appear from the vacuum and then annihilate. These virtual particles contribute to physical processes like the Casimir effect and the anomalous magnetic moment of the electron. They are not directly observable, but their effects are real and measurable. Virtual particles populate Feynman diagrams, pictorial representations of particle interactions in quantum field theory. Though they exist only ephemerally, they play crucial roles in calculations and help physicists understand fundamental processes. Quantum biology explores whether quantum effects are significant in living systems. For decades, biology operated mostly on classical principles, with quantum mechanics relevant only at the molecular level for bond formation. Recent research suggests quantum coherence and entanglement might play roles in photosynthesis, bird navigation, enzyme reactions, and possibly even consciousness. In photosynthesis, quantum superposition may allow plants to explore multiple energy transfer pathways simultaneously, finding the most efficient route before collapsing to a single pathway. Some birds may sense Earth's magnetic field using quantum entanglement in specialized proteins in their eyes. These discoveries are still debated, but they indicate that the boundary between quantum and classical worlds may be more fluid than once thought. The measurement problem is one of the deepest mysteries in quantum mechanics. The theory predicts that unobserved quantum systems evolve smoothly according to the Schrödinger equation, maintaining superpositions. But when a measurement occurs, the superposition collapses to a single outcome. What constitutes a measurement? Does consciousness play a role? Does the wave function physically collapse? Or does the universe split as in the many worlds interpretation? These questions remain unresolved. Different interpretations offer different answers, but none is universally accepted. The measurement problem highlights the gap between the mathematical formalism of quantum mechanics and our intuitive understanding of reality. Schrödinger's cat is a thought experiment illustrating the absurdity of applying quantum superposition to macroscopic objects. Schrödinger imagined a cat in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers and breaks the vial, killing the cat. Quantum mechanics says that until observed, the atom is in a superposition of decayed and not decayed states. This would place the cat in a superposition of alive and dead, an obviously ridiculous situation. Schrödinger used this paradox to criticize the Copenhagen interpretation. In reality, quantum decoherence ensures that macroscopic objects like cats do not remain in superposition. Interactions with the environment rapidly collapse the wave function. The thought experiment remains a powerful illustration of the measurement problem. The no-cloning theorem states that it is impossible to create an exact copy of an unknown quantum state. If you have a quantum system in some state, but do not know what that state is, no physical process can produce a perfect duplicate. This theorem has profound implications. It means quantum information cannot be copied like classical information, which is the basis for the security of quantum cryptography. It also prevents faster-than-light communication using entanglement, because you cannot clone the quantum state of one entangled particle and send copies elsewhere. The no-cloning theorem, proven in 1982, reflects fundamental differences between quantum and classical information. Quantum spin is a form of intrinsic angular momentum carried by particles. Unlike the spinning of a planet on its axis, quantum spin is not associated with physical rotation. It is an inherent property, like mass or charge. Electrons, protons, and neutrons have spin 1/2, meaning their spin angular momentum comes in two discrete values, often called spin up and spin down. Photons have spin 1. The values are quantized, restricted to integer or half-integer multiples of a fundamental unit. Spin has no classical analog, yet it is essential for understanding atomic structure, magnetism, and particle interactions. Measuring spin in one direction randomizes the spin in perpendicular directions, illustrating the uncertainty principle. Fermions and bosons are the two fundamental classes of particles. Fermions have half-integer spin and obey the Pauli exclusion principle, meaning no two identical fermions can occupy the same quantum state. Electrons, protons, neutrons, and quarks are fermions. Bosons have integer spin and do not obey the exclusion principle. Many bosons can occupy the same quantum state, leading to phenomena like lasers and Bose-Einstein condensates. Photons, gluons, and W and Z bosons are fundamental bosons. The Higgs boson is also a boson. The distinction between fermions and bosons is crucial for understanding matter and forces. A Bose-Einstein condensate is a state of matter formed when a gas of bosons is cooled to temperatures near absolute zero. At these extremely low temperatures, a large fraction of the atoms occupy the lowest quantum state, behaving collectively as a single quantum entity. The atoms lose their individual identities and quantum effects become visible on macroscopic scales. Bose-Einstein condensates can exhibit phenomena like superfluidity, where the fluid flows without viscosity. The existence of this state was predicted by Albert Einstein and Satyendra Nath Bose in the 1920s. But the first condensate was not created until 1995. Eric Cornell and Carl Wieman at Gila and Wolfgang Kettel at MIT independently achieved this feat, for which they shared the Nobel Prize in Physics in 2001. Their success required cooling atoms to within a fraction of a degree above absolute zero, using sophisticated laser and magnetic techniques. Superfluidity is a phase of matter with zero viscosity. A superfluid can flow through narrow channels without resistance and can climb the walls of containers, seemingly defying gravity. Helium-4 becomes a superfluid below 2.2 Kelvin. This behavior arises because the helium atoms, which are bosons, occupy the same quantum state, forming a coherent quantum fluid. Superfluidity demonstrates quantum mechanics on a macroscopic scale, where effects normally confined to atoms become visible. It was discovered by Piotr Kapitsa in helium in 1937, earning him the Nobel Prize in Physics in 1978. Superconductivity is the phenomenon where certain materials conduct electricity with zero resistance below a critical temperature. When cooled sufficiently, electrons in the material form pairs called Cooper pairs, which behave collectively as bosons. These pairs form a coherent quantum state that flows without scattering off impurities or defects in the material. Superconductors also expel magnetic fields from their interior, a phenomenon called the Meissner effect. Superconductivity was discovered by Heike Kamerlingh-Onnes in 1911, when he observed Mercury's electrical resistance vanish at temperatures near 4 Kelvin. The microscopic explanation came much later, when John Bardeen, Leon Cooper, and John Schrieffer developed BCS theory in the 1950s, earning them the Nobel Prize in Physics in 1972. High-temperature superconductors, discovered in the 1980s by Georg Bednorz and Alex Müller, operate at temperatures above liquid nitrogen, greatly expanding potential applications in power transmission, medical imaging, and transportation. Quantum phase transitions occur at absolute zero and are driven by quantum fluctuations rather than thermal energy. In classical phase transitions, like water freezing, temperature drives the change. In quantum phase transitions, tuning a parameter like pressure or magnetic field changes the ground state of the system. These transitions reveal the competition between different quantum states and can lead to exotic phases of matter with unusual properties. Understanding quantum phase transitions helps physicists explore materials like superconductors and quantum magnets. They also have connections to black hole physics and cosmology. Anyons are particles that exist only in two-dimensional systems and have fractional statistics intermediate between fermions and bosons. In 3 dimensions, exchanging two identical particles results in the wave function acquiring a phase of +1 for bosons or -1 for fermions. In 2 dimensions, more possibilities exist. Exchanging anyons can result in a wave function that acquires any phase, hence the name. Anyons have been observed in the fractional quantum Hall effect and are of interest for topological quantum computing, where quantum information is stored in the braiding patterns of anyons, making it resistant to decoherence. The quantum Zeno effect shows that frequent measurements can freeze the evolution of a quantum system. Normally, a quantum state evolves continuously, but if you measure the state repeatedly, each measurement collapses the wave function back to the initial state, preventing the system from evolving. This counterintuitive effect has been observed experimentally and is named after Zeno's paradoxes from ancient Greek philosophy. It has implications for quantum error correction and controlling quantum systems, and it illustrates the profound role measurement plays in quantum mechanics. Quantum chaos studies how chaotic classical systems behave in the quantum realm. Classical chaos involves extreme sensitivity to initial conditions, where tiny differences grow exponentially, making long-term prediction impossible. Quantum mechanics is deterministic at the level of wave function evolution, so traditional chaos does not occur. However, quantum systems corresponding to classically chaotic systems exhibit signatures of chaos in energy level statistics, wave function structure, and response to perturbations. Understanding quantum chaos is important for everything from atomic physics to quantum computing, and it bridges the gap between classical and quantum descriptions of complex systems. Quantum walks are the quantum analog of random walks. In a classical random walk, a particle steps left or right with equal probability at each step. In a quantum walk, the particle can be in a superposition of multiple positions, leading to interference effects. Quantum walks spread faster than classical random walks, and this speed-up is thought to underlie many quantum algorithms. They provide a framework for designing new quantum algorithms and simulating quantum systems. Quantum walks have been implemented experimentally using photons, ions, and atoms, demonstrating quantum behavior in controlled settings. Quantum annealing is a computational method for finding the lowest energy state of a system. It exploits quantum tunneling to explore the energy landscape more efficiently than classical approaches. The system is initialized in a superposition of all possible states and slowly evolved, allowing it to tunnel through energy barriers that would trap classical algorithms. Quantum annealing is used in optimization problems, machine learning, and materials science. Companies like D-Wave have built quantum annealers with thousands of qubits, though debate continues about the extent of their quantum advantage over classical computers. Topological quantum computing uses anyons and topological properties of quantum states to store and manipulate information. The idea is to encode information not in the state of individual particles, but in the overall braiding pattern of anyons moving around each other. This topological encoding is intrinsically resistant to local errors because disturbing one anyon does not change the global pattern. Topological quantum computers could be more robust than conventional quantum computers, which are fragile and require extensive error correction. Though still largely theoretical, progress is being made in creating materials that support anyone's and demonstrating topological phenomena. Quantum dots are nanoscale semiconductor particles that confine electrons in 3 dimensions. Because of their tiny size, electrons occupy discrete energy levels like in atoms, earning quantum dots the nickname artificial atoms. The energy levels depend on the dot's size, allowing their optical properties to be tuned. Quantum dots emit light of specific colors when excited, and they are used in displays, solar cells, biological, imaging, and quantum computing. They provide a controllable system for studying quantum mechanics and have wide-ranging practical applications. Quantum error correction protects quantum information from decoherence and other errors. Qubits are fragile and easily disturbed by their environment. Simple error correction schemes from classical computing do not work because measuring a qubit collapses its state and you cannot clone quantum information. Quantum error correction encodes one logical qubit into multiple physical qubits, spreading the information across them so that errors can be detected and corrected without learning the encoded information. Schemes like the surface code show promise for building fault-tolerant quantum computers. Developing practical quantum error correction is one of the key challenges in realizing large-scale quantum computing. Quantum algorithms are procedures designed to run on quantum computers and solve problems more efficiently than classical algorithms. Shor's algorithm can factor large numbers exponentially faster than the best-known classical algorithms, threatening current cryptographic systems. Grover's algorithm searches unstructured databases with a quadratic speedup. Quantum simulation algorithms model quantum systems that are intractable for classical computers, with applications in chemistry, materials science, and fundamental physics. Discovering new quantum algorithms is an active area of research, as scientists explore what problems quantum computers can solve better than classical ones. Quantum supremacy refers to demonstrating that a quantum computer can perform a specific task that would be impractical for classical computers to complete in a reasonable time. In 2019, Google announced achieving quantum supremacy with a 54-qubit processor called Sycamore that performed a specialized calculation in about 200 seconds. They claimed the same task would take the world's most powerful supercomputers thousands of years, though this estimate was later disputed by IBM and others, who suggested classical computers could solve it faster than initially claimed. The term itself has generated debate, and some prefer quantum advantage to describe such demonstrations. While these experiments mark important milestones, they do not mean quantum computers are better at all tasks. Rather, they show quantum advantage on carefully chosen problems and represent progress toward practical quantum computing that could solve useful real-world problems. The Stern-Gerlach experiment demonstrated space quantization and the existence of spin. In 1922, Otto Stern and Walter Gerlach passed a beam of silver atoms through a non-uniform magnetic field. Classically, the magnetic moments should be oriented randomly, producing a continuous distribution on the detector. Instead, The beam split into two discrete spots, showing that angular momentum components are quantized. This was one of the first direct evidences of quantum mechanics and revealed the property now called spin. The experiment profoundly influenced the development of quantum theory. Quantum interference occurs when different paths or states combine, with amplitudes adding according to their relative phases. Constructive interference happens when amplitudes reinforce, increasing the probability of an outcome. Destructive interference happens when amplitudes cancel, reducing or eliminating the probability. Interference is the hallmark of wave behavior and central to understanding quantum mechanics. It underlies the double-slit experiment, quantum computing, and many other quantum phenomena. Controlling interference is key to building quantum devices. The correspondence principle states that quantum mechanics must reproduce classical physics in the appropriate limit. Proposed by Niels Bohr, it asserts that for large quantum numbers or high energies, quantum predictions should match classical predictions. This principle guided early developments in quantum theory, ensuring consistency with established physics. It remains important when translating classical problems into quantum frameworks and checking that new theories are compatible with known results in limiting cases. Quantum mechanics successfully explains the structure of atoms. Electrons occupy discrete orbitals characterized by quantum numbers. The shapes of these orbitals, determined by solving the Schrödinger equation, account for chemical bonding and the periodic table. The quantum model explains why atoms are stable, why they emit and absorb light at specific wavelengths, and how they interact to form molecules. Before quantum mechanics, atomic structure was a mystery. Now it is understood in exquisite detail. Quantum chemistry applies quantum mechanics to understand molecules and chemical reactions. By solving the Schrödinger equation for multi-electron systems, chemists predict molecular structures, bond energies, reaction rates, and spectroscopic properties. Computational methods like density functional theory allow practical calculations on complex molecules, guiding drug discovery, materials design, and catalysis. Quantum chemistry bridges physics and chemistry, showing that all chemical phenomena emerge from quantum mechanical principles governing electrons and nuclei. Molecular orbital theory describes bonding in molecules using quantum mechanics. When atoms combine, their atomic orbitals overlap and form molecular orbitals extending over the entire molecule. Electrons occupy these molecular orbitals, which can be bonding, lowering the energy and stabilizing the molecule, or antibonding, raising the energy. Molecular orbital theory explains phenomena like resonance, magnetism, and electrical conductivity in molecules. It provides a framework for understanding chemical reactions and predicting properties of new compounds. Quantum tunneling plays a crucial role in nuclear fusion in stars. Protons in stellar cores have high energies due to temperature, but classically, they still lack sufficient energy to overcome the electrostatic repulsion between positively charged nuclei. Quantum tunneling allows protons to penetrate the Coulomb barrier with some probability, enabling fusion reactions that power the Sun. Without tunneling, stars would not shine, and elements heavier than hydrogen would not form. Life depends on quantum mechanics operating at the heart of every star. Radioactive alpha decay is driven by quantum tunneling. An alpha particle, consisting of 2 protons and 2 neutrons, inside a nucleus is trapped by the nuclear force. Classically, it does not have enough energy to escape. Quantum mechanically, the particle's wave function extends beyond the nuclear potential, giving a small probability of tunneling out. Once outside, the alpha particle is repelled by the positive nucleus and flies away. The rate of alpha decay depends exponentially on the barrier properties, explaining the wide range of half-lives among radioactive isotopes. Tunnel diodes exploit quantum tunneling for extremely fast switching. In a heavily doped PN junction, the barrier is thin enough that electrons can tunnel through it. At certain voltages, tunneling current dominates, producing a region where current decreases as voltage increases, a negative resistance effect. This allows tunnel diodes to switch on and off in picoseconds, making them useful in high-frequency applications. Though largely replaced by other technologies, tunnel diodes remain a beautiful demonstration of quantum mechanics in electronics. Flash memory relies on quantum tunneling to store data. Each memory cell contains a floating gate surrounded by insulating layers. Electrons are injected onto the gate through tunneling when a voltage is applied. Once trapped, they change the cell's threshold voltage, representing stored data. To erase data, a voltage causes electrons to tunnel back off the gate. Flash memory's ability to retain data without power and its speed and reliability owe directly to quantum tunneling. Quantum mechanics explains the specific heat of solids. Classical theory predicts that specific heat should be bar constant, but experiments show it decreases at low temperatures. Einstein and later Debye showed that lattice vibrations are quantized as phonons, quanta of vibrational energy. At low temperatures, only low-energy phonons are excited, reducing the heat capacity. This quantum treatment accurately describes observed behavior and was an early success for quantum theory in condensed matter physics. Quantum mechanics is essential for understanding semiconductors. The band structure of semiconductors, crucial for their electronic properties, arises from quantum mechanical treatment of electrons in periodic lattices. The energy gap between the valence and conduction bands determines whether a material is a conductor, insulator, or semiconductor. Doping introduces impurities that alter electronic properties in controlled ways. Transistors, diodes, and integrated circuits depend on this quantum mechanical understanding. Modern electronics would be impossible without quantum mechanics. Quantum mechanics predicts the properties of lasers. Lasers produce coherent light through stimulated emission, where photons induce atoms in excited states to emit additional identical photons. This process relies on quantum mechanical energy levels and transition probabilities. The coherence and monochromatic nature of laser light stem from quantum principles. Lasers have countless applications, From telecommunications and surgery to barcode scanners and scientific research, they are among the most practical manifestations of quantum mechanics. The quantum Hall effect reveals topological properties of electronic states. When a two-dimensional electron gas is subjected to a strong magnetic field at low temperature, the Hall resistance exhibits plateaus at quantized values. These plateaus are extraordinarily precise, independent of sample details. The effect arises from quantized energy levels called Landau levels and topological invariants characterizing the electronic wave functions. Klaus von Klitzing received the Nobel Prize in Physics in 1985 for discovering the integer quantum Hall effect. The fractional quantum Hall effect, discovered later, involves exotic quantum correlations. Graphene is a single layer of carbon atoms arranged in a hexagonal lattice and exhibits remarkable quantum properties. Electrons in graphene behave as massless Dirac fermions, moving at a constant velocity independent of energy. This leads sometimes to unusual electronic properties like ultra-high conductivity and the ability to manipulate electrons with electric fields. Graphene's quantum Hall effect occurs even at room temperature. Its strength and flexibility make it promising for applications in electronics, materials science, and nanotechnology. Andrei Geim and Konstantin Novoselov received the Nobel Prize in Physics in 2010 for isolating graphene. Quantum mechanics governs the structure of neutron stars. In these incredibly dense remnants of supernova explosions, gravity compresses matter to nuclear densities. Electron degeneracy pressure, arising from the Pauli exclusion principle, initially resists collapse. At higher densities, electrons combine with protons to form neutrons, and neutron degeneracy pressure supports the star. The entire neutron star can be viewed as a giant atomic nucleus. Understanding neutron stars requires quantum mechanics, general relativity, and nuclear physics, probing matter under extreme conditions unreachable in laboratories. Quantum mechanics plays a role in the early universe. In the first moments after the Big Bang, quantum fluctuations in the inflaton field seeded the density variations that grew into galaxies and large-scale structure. Quantum mechanics operating on microscopic scales influenced the evolution of the entire cosmos. The cosmic microwave background radiation carries imprints of these quantum fluctuations, providing observational evidence. Quantum field theory in curved spacetime, combining quantum mechanics and general relativity, describes these processes. Hawking radiation is a theoretical prediction that black holes should emit particles due to quantum effects near the event horizon. Stephen Hawking calculated in 1974 that quantum vacuum fluctuations near a black hole could lead to particle-antiparticle pairs forming at the edge of the event horizon. One particle might fall into the black hole while the other escapes. From far away, this would appear as though the black hole emits radiation. This process would cause black holes to lose mass gradually and eventually evaporate completely. Because the predicted radiation is extremely faint, especially for stellar mass and larger black holes, it has never been directly observed. However, analogues of Hawking radiation have been created in laboratory systems. The concept has profound implications for black hole thermodynamics and represents an important intersection between quantum mechanics and gravity, though it remains an unconfirmed prediction awaiting observational evidence. Quantum information theory studies how quantum mechanics affects information processing. Qubits can be entangled and exist in superposition, allowing new kinds of computation and communication impossible with classical bits. Quantum entanglement enables correlations stronger than any classical correlation. Quantum teleportation transfers quantum states without transmitting particles. Quantum cryptography provides unconditional security. These capabilities have led to the field of quantum information science, uniting physics, computer science, and mathematics to explore the fundamental limits of information. The black hole information paradox questions whether information is lost when matter falls into a black hole. Quantum mechanics dictates that information cannot be destroyed, yet black holes appear to obliterate all information about matter they swallow. Hawking radiation seems thermal and carries no information, suggesting information is lost. This conflicts with quantum mechanics. Resolutions have been proposed, involving quantum entanglement, holography, and modifications to our understanding of space-time. But the paradox remains unresolved. It highlights tensions between quantum mechanics and general relativity, and may point toward a deeper theory of quantum gravity. String theory is a theoretical framework attempting to reconcile quantum mechanics with general relativity. It proposes that fundamental particles are not point-like, but tiny vibrating strings, whose different vibration modes correspond to different particles. The theory naturally incorporates gravity and aims to unify all fundamental forces within a single mathematical framework. It predicts spatial dimensions beyond the three we experience and describes exotic objects called brains. Despite its mathematical elegance and promise, string theory has faced criticism for lacking testable predictions that have been confirmed by experiment. After decades of development, no direct experimental evidence supports its core claims, though it has produced valuable mathematical insights. String theory remains one approach to quantum gravity among several competing frameworks, valued by some researchers for its theoretical richness, while questioned by others for its empirical inaccessibility. Loop quantum gravity is an alternative approach to quantum gravity. It quantizes space-time itself, suggesting that space is made of discrete loops forming a spin network. At the Planck scale, space-time becomes granular. Loop quantum gravity preserves the background independence of general relativity and does not require extra dimensions. It predicts phenomena like the quantization of area and volume. Testing loop quantum gravity is challenging because effects manifest at the Planck scale, far beyond current experimental reach. It offers a different vision of quantum spacetime than string theory. Quantum mechanics has been tested to extraordinary precision. The magnetic moment of the electron agrees with quantum electrodynamics calculations to better than 1 part in a trillion. Atomic clocks based on quantum transitions are the most precise timekeeping devices ever made, accurate to 1 second in billions of years. Quantum mechanics predicts phenomena that have been verified in countless experiments across all branches of physics. Despite its counterintuitive nature, quantum mechanics is one of the most successful and well-confirmed theories in science. Its predictions have never been proven wrong. The future of quantum mechanics lies in technology and deeper understanding. Quantum computers promise to revolutionize computing, solving problems in cryptography, optimization, and simulation intractable for classical machines. Quantum sensors could measure gravitational waves, map neural activity, or detect dark matter. Quantum communication networks may create unhackable global communication systems. Meanwhile, fundamental questions about measurement, reality, and the quantum classical boundary continue to intrigue physicists. Experiments probing quantum mechanics in new regimes, from massive particles to cosmological scales, may reveal new physics or confirm that quantum mechanics applies universally. The quantum world remains a frontier of discovery. The Wheeler delayed choice experiment reveals puzzling aspects of quantum measurement. Proposed by John Wheeler in the 1970s, and later demonstrated experimentally, this variation of the double-slit experiment allows the experimenter to decide whether to observe which path information after a photon has already passed through the slits. The results suggest that what we choose to measure in the present appears to determine whether the photon exhibited wave or particle behavior in the past. This does not enable backward time travel or causality violations. Rather, it demonstrates that quantum events do not possess definite properties until measured. The experiment challenges our classical intuitions about temporal order, suggesting that the act of measurement plays a more fundamental role than simply revealing pre-existing facts. Quantum Darwinism explains how the classical world emerges from quantum mechanics. Wojciech Zurek proposed that environmental interactions cause many copies of certain quantum states to proliferate, like successful species in natural selection. These are the states we observe as classical. Information about a quantum system becomes redundantly encoded in the environment through decoherence. When we observe an object, we sample this redundant information, which is why different observers agree on classical properties. States that don't proliferate remain quantum and unobservable at macroscopic scales. Quantum Darwinism bridges quantum and classical physics, explaining objectivity and the emergence of a shared reality. The Aharonov-Bohm effect demonstrates that electromagnetic potentials have physical significance, even where fields vanish. In classical electromagnetism, only electric and magnetic fields affect charged particles. Yakov Aharonov and David Bohm predicted in 1959 that electrons could be influenced by electromagnetic potentials in regions where the fields themselves are zero. Experiments confirmed this. An electron beam split and recombined around a solenoid containing magnetic flux, shows an interference pattern that depends on the flux, even though the magnetic field is confined inside the solenoid where electrons never travel. This revealed that potentials, not just fields, are fundamental in quantum mechanics and influenced gauge theory development. Quantum contextuality means that measurement outcomes depend on which other measurements are made simultaneously. You cannot assign definite pre-existing values to all observables of a quantum system independent of the measurement context. The value you measure for one property can depend on which other properties you choose to measure at the same time. This was proven rigorously by theorems like the Cauchy-Specker theorem. Contextuality has no classical analog and shows that quantum systems are fundamentally different from classical objects that possess all properties simultaneously. It constrains hidden variable theories and is a resource for quantum computing. Quantum metrology uses quantum properties to make measurements more precise than classical methods allow. Entangled states and squeezed light can improve the sensitivity of instruments, measuring time, position, magnetic fields, and other quantities. Atomic clocks use quantum superpositions of atomic states to achieve precisions better than 1 part in 10 to the 18th. Gravitational wave detectors like LIGO use squeezed light to reduce quantum noise and improve sensitivity. Quantum sensors have applications in medicine, geology, defense, and fundamental physics. They push measurement precision to the fundamental limits set by quantum mechanics itself. The quantum eraser experiment shows that erasing Witch path information restores interference even after the particle has been detected. In a modified double-slit setup, detectors are placed to determine which slit each particle passes through, destroying the interference pattern. Additional apparatus then erases this information before it can be permanently recorded. When this happens, the interference pattern reappears in the appropriate subset of detected particles. This demonstrates that the wave or particle behavior depends not just on whether a measurement was made, but on whether the information is available in principle. The quantum eraser deepens the mystery of the observer's role in quantum mechanics. Quantum game theory extends game theory by allowing players to use quantum strategies involving superposition and entanglement. Classical game theory analyzes strategic interactions where players make choices leading to payoffs. In quantum games, players can place their strategies in superposition or entangle their choices with opponents. This can fundamentally alter the equilibrium outcomes. For example, in the prisoner's dilemma, quantum strategies allow both players to cooperate and achieve better outcomes than classical mixed strategies permit. Quantum game theory has applications in economics, biology, and understanding competitive interactions in quantum systems. It shows how quantum mechanics changes not just physics, but also reasoning about strategic behavior. Quantum money is a theoretical form of currency that would exploit the no-cloning theorem to prevent counterfeiting. Each quantum money state would be a unique quantum state that cannot be copied perfectly due to fundamental laws of quantum mechanics. A bank could verify the money's authenticity by measuring it in a specific basis known only to the bank. Because the no-cloning theorem prevents perfect copying of unknown quantum states, counterfeiters would be unable to duplicate the money. While the concept is mathematically sound and demonstrates important differences between quantum and classical information, practical quantum money faces formidable technological challenges and has not been implemented outside of research laboratories. The idea contributes to broader research into quantum communication protocols and cryptography. Quantum radar is a developing technology that aims to use entangled photons to detect objects with potentially greater sensitivity than classical radar. The concept involves sending one photon from an entangled pair toward a target while keeping the other at the source. Reflected photons from the target would be compared with the retained photon, with quantum correlations potentially surviving even in noisy environments. This could improve detection of low reflectivity targets and allow operation at lower power, making the radar harder to detect. The technology could also help distinguish targets from background noise more effectively. While the basic principles have been demonstrated in laboratory settings, practical quantum radar systems face significant technical challenges and remain under development. The concept represents an ambitious application of quantum entanglement to sensing and potential defense applications. Quantum illumination is a technique for detecting objects using quantum correlations between signal and reference beams. It provides advantages in target detection at low signal-to-noise ratios, especially in lossy or noisy environments. By exploiting entanglement between photons sent toward a target and photons retained as a reference, quantum illumination achieves better sensitivity than classical methods. This has implications for biomedical imaging, security screening, and remote sensing. It demonstrates that quantum mechanics offers practical advantages even in systems where entanglement itself does not survive to the detector. The quantum pigeonhole principle states that quantum mechanics can violate classical pigeonhole reasoning. Classically, if you put 3 pigeons into 2 holes, at least 2 pigeons must share a hole. Quantum mechanically, particles can avoid this conclusion. Experiments have demonstrated scenarios where 3 particles in 2 states behave as if no 2 particles occupy the same state, violating the classical pigeonhole principle. This counterintuitive result emerges from pre- and post-selection of quantum states and highlights how deeply quantum mechanics differs from classical logic. It challenges our basic notions of counting and containment at the quantum level. Quantum discord is a measure of quantum correlations that goes beyond entanglement. 2 quantum systems can be correlated in ways that are neither classical nor entangled. These correlations, quantified by quantum discord, reflect the disturbance caused by local measurements on one system affecting the other. Discord exists even in separable states that are not entangled, suggesting that quantum correlations are richer than entanglement alone captures. Quantum discord may be a resource for certain quantum information tasks and helps clarify which aspects of quantumness are responsible for advantages over classical systems. Quantum steering is a form of correlation intermediate between entanglement and Bell non-locality. Alice's measurements on her part of an entangled system can influence or steer the state of Bob's part, demonstrating quantum correlations. Steering is weaker than violating Bell inequalities, but stronger than mere entanglement. It was introduced by Schrödinger alongside entanglement, but only recently has been rigorously defined and experimentally demonstrated. Quantum steering has applications in cryptography and tests of quantum mechanics, offering insights into the structure of quantum correlations and the boundary between quantum and classical worlds. Weak measurements allow limited information to be extracted from quantum systems without fully collapsing the wave function. By using weak interaction between the measurement apparatus and the system, you can gather partial information while leaving the superposition mostly intact. Multiple weak measurements can be combined statistically to learn about properties that strong measurements would destroy. Weak measurements have revealed surprising effects like weak values, which can lie outside the range of eigenvalues, providing amplification of small signals. They are used in precision measurements, quantum foundations research, and developing new quantum technologies. The quantum kicked rotor is a paradigm system for studying quantum chaos. A particle on a ring receives periodic kicks that would classically induce chaotic motion. Quantum mechanically, interference effects lead to localization, where the particle's momentum distribution stops spreading despite the kicks. This dynamical localization is analogous to Anderson localization in disordered systems. The quantum kicked rotor has been realized experimentally using cold atoms and provides insights into how quantum mechanics suppresses chaos, a phenomenon important for understanding stability in atomic and molecular systems, and the quantum classical transition. Quantum scarring refers to enhanced probability densities along classical periodic orbits in quantum systems that are classically chaotic. While quantum mechanics delocalizes wave functions in chaotic systems, certain eigenstates show concentrations along unstable periodic orbits of the classical system. Discovered in the late 1980s, quantum scars are a signature of classical chaos in quantum systems. Recently, scars have been observed in many body quantum systems, affecting thermalization and potentially providing long-lived states useful for quantum information storage. Quantum thermodynamics extends thermodynamics to quantum systems and explores how quantum mechanics modifies concepts like work, heat, and entropy. At the quantum scale, fluctuations become significant, and definitions from classical thermodynamics must be refined. Quantum thermodynamics investigates the limits of energy conversion, the role of information in thermodynamics, and whether quantum effects can enhance heat engine efficiency. It also explores the thermodynamics of quantum information, connecting entropy to entanglement and coherence. This field has implications for nanotechnology, quantum computing, and understanding the foundations of statistical mechanics. The quantum refrigerator uses quantum coherence to cool systems below temperatures achievable by classical methods. Quantum heat engines and refrigerators exploit superposition and entanglement to transfer heat in ways unavailable classically. These devices challenge the traditional formulations of thermodynamic laws at the quantum scale. Research into quantum thermodynamic machines explores the efficiency limits of quantum engines and the role of quantum correlations in thermodynamic processes. Though mostly theoretical, quantum refrigerators could eventually cool systems for quantum computers and sensors, where traditional cooling methods reach fundamental limits. The quantum Rabi model describes the simplest interaction between light and matter, a two-level atom coupled to a single mode of the electromagnetic field. Despite its simplicity, the model exhibits rich physics, including vacuum Rabi splitting, where energy levels split due to strong coupling between the atom and field. It captures the essence of light-matter interaction underlying lasers, masers, and cavity quantum electrodynamics. The quantum Rabi model has been realized in various physical systems and serves as a testing ground for quantum optics phenomena, quantum simulations, and understanding fundamental aspects of quantum field theory in controlled settings. Cavity quantum electrodynamics studies the interaction between atoms and photons confined in optical cavities. When an atom is placed inside a mirrored cavity, the modes of the electromagnetic field are restricted, modifying how the atom emits and absorbs light. Strong coupling between the atom and cavity mode leads to phenomena like the vacuum Rabi oscillation, where energy sloshes back and forth between atom and field even in the absence of photons initially. Cavity QED has applications in quantum computing, where atoms or artificial atoms like superconducting qubits interact with microwave or optical cavities to process quantum information. Photonic quantum computing uses photons as qubits, exploiting their long coherence times and fast manipulation speeds. Linear optical quantum computing employs beam splitters, phase shifters, and photodetectors to perform quantum gates. Photons interact weakly with the environment, reducing decoherence, but they also interact weakly with each other, making two-qubit gates challenging. Techniques like measurement-based quantum computing and boson sampling circumvent these difficulties. Photonic quantum computers have demonstrated advantages for specific tasks and are promising for quantum communication and distributed quantum computing, where photons naturally transmit information over long distances. Boson sampling is a computational task believed to be hard for classical computers, but feasible for quantum devices. It involves sampling from the output distribution of non-interacting bosons passing through a network of beam splitters. Boson sampling does not require universal quantum computing capabilities, but still demonstrates quantum advantage for a specific problem. Experiments with dozens of photons have been performed, approaching the regime where classical simulation becomes impractical. Boson sampling is a test of quantum complexity theory and a step toward practical quantum computers that outperform classical machines. Trapped ion quantum computers use individual ions held by electromagnetic fields as qubits. Ions are excellent qubits because they can be isolated from the environment, have long coherence times, and their quantum states can be precisely controlled with lasers. 2-qubit gates are performed by entangling the ions' motional states, coupling their internal quantum states indirectly. Trapped ion quantum computers have achieved high gate fidelities and implemented small-scale quantum algorithms. Companies and research groups worldwide are scaling up trapped ion systems, working toward fault-tolerant quantum computers that can solve problems beyond the reach of classical machines. Superconducting quantum computers are among the most advanced quantum computing platforms. They use superconducting circuits with Josephson junctions as qubits, operating at temperatures near absolute zero, where superconductivity emerges. These artificial atoms can be fabricated using techniques from semiconductor industry and controlled with microwave pulses. Superconducting qubits have relatively short coherence times compared to trapped ions, but they can be manufactured on chips and scaled to many qubits. Companies like IBM, Google, and Rigetti have built superconducting quantum processors with tens to hundreds of qubits. Google's claim of quantum supremacy in 2019 used a superconducting quantum computer. The challenge lies in reducing errors and improving coherence to enable large-scale, fault-tolerant quantum computation. Quantum neural networks combine quantum computing with machine learning. By representing data and parameters as quantum states and using quantum gates to process them, quantum neural networks can potentially learn patterns more efficiently than classical neural networks for certain tasks. Quantum advantages might arise from exploiting superposition and entanglement to explore high-dimensional parameter spaces. Applications include pattern recognition, optimization, and generative modeling. Research is ongoing to determine where quantum neural networks offer genuine advantages and how to train them effectively on near-term quantum devices. Quantum machine learning explores using quantum algorithms to speed up machine learning tasks. Algorithms like the quantum support vector machine and quantum principal component analysis promise exponential speed-ups for specific data analysis problems. Quantum computers could efficiently solve linear systems of equations, perform clustering, and optimize complex functions underlying machine learning. However, challenges include loading classical data into quantum states efficiently and ensuring quantum advantage persists in practical scenarios with noisy hardware. Quantum machine learning is a rapidly growing field combining quantum information, computer science, and statistics, seeking to harness quantum mechanics for artificial intelligence. Variational quantum algorithms are hybrid approaches, combining classical and quantum computers to solve optimization problems. The quantum computer prepares a parameterized quantum state and measures an observable, yielding a cost function. The classical computer adjusts the parameters to minimize the cost. This iterative process continues until convergence. Variational algorithms like the quantum approximate optimization algorithm and the variational quantum eigensolver are designed for near-term quantum devices with limited qubit counts and coherence. They have applications in chemistry, materials science, and combinatorial optimization, representing a practical path toward useful quantum computing before fault-tolerant machines are available. The quantum approximate optimization algorithm seeks to find optimal solutions to combinatorial problems. It prepares a superposition of possible solutions and applies alternating quantum gates inspired by quantum annealing. By tuning parameters through classical optimization, the algorithm enhances the probability of measuring good solutions. Though it does not guarantee finding the global optimum, QAOA can outperform classical heuristics for certain problems. It exemplifies how quantum computers might tackle NP-hard optimization problems important in logistics, finance, and scheduling, even on near-term devices with modest qubit numbers and coherence times. Quantum simulation uses quantum computers to model quantum systems that are intractable for classical computers. Simulating chemical reactions, superconductors, or magnetic materials requires solving the Schrödinger equation for many interacting particles. Classical computers struggle because the computational cost grows exponentially with system size. Quantum computers, being quantum systems themselves, can efficiently simulate other quantum systems. Richard Feynman originally proposed this idea in the 1980s. Quantum simulators can predict material properties, design catalysts, understand high-temperature superconductors, and explore fundamental physics, accelerating discoveries in chemistry and materials science. The variational quantum eigensolvers is an algorithm for finding the ground state energy of molecules. It prepares a trial wave function on a quantum computer and measures the system's energy. Classical optimization adjusts the wave function parameters to minimize the energy, approximating the ground state. VQE has been demonstrated on small molecules like hydrogen and lithium hydride, achieving chemical accuracy on noisy quantum hardware. As quantum computers improve, VQE could design new drugs, materials, and catalysts by predicting molecular properties beyond the reach of classical computational chemistry methods. Quantum chemistry calculations on quantum computers promise to revolutionize drug discovery and materials design. Understanding how atoms bond and react requires solving quantum mechanics for electrons in molecules. For complex molecules, classical approximations become inaccurate or computationally prohibitive. Quantum computers can simulate electronic structure directly, predicting reaction rates, binding energies, and molecular spectra with high precision. This could accelerate finding new pharmaceuticals, optimizing catalysts for clean energy, designing better batteries, and developing advanced materials. The intersection of quantum computing and chemistry represents one of the most promising near-term applications with profound societal impact. Nitrogen vacancy centers in diamond are defects in the diamond lattice that create atomic-scale quantum systems useful for sensing and quantum computing. The nitrogen vacancy center consists of a nitrogen atom adjacent to a vacant lattice site, creating electron spins that can be manipulated with light and microwaves at room temperature. These spins are sensitive to magnetic fields, electric fields, and temperature, enabling ultra-precise sensors. NV centers can be used to image magnetic fields at the nanoscale, study biological systems, detect single protein molecules, and measure neural activity. They also serve as qubits for quantum computers and nodes for quantum networks, showcasing versatility in quantum technologies. Quantum networks distribute quantum information between distant nodes using photons transmitted through optical fibers or free space. Entanglement can be shared across the network, enabling distributed quantum computing, secure communication, and enhanced sensing. Quantum repeaters extend the range by overcoming photon loss through entanglement, swapping, and quantum error correction. Building a quantum internet faces challenges, including photon loss, maintaining coherence, and interfacing different quantum systems. However, small-scale quantum networks have been demonstrated, and research toward a global quantum internet continues. Such a network would revolutionize communication, providing unconditional security and enabling new forms of distributed quantum computing. Quantum cryptanalysis explores how quantum computers threaten current cryptographic systems. Shor's algorithm efficiently factors large numbers, breaking widely used public key encryption schemes like RSA. This motivates the development of post-quantum cryptography, encryption methods resistant to quantum attacks. Grover's algorithm provides quadratic speedup for brute force searches, affecting symmetric key cryptography but less severely. Quantum computers also enable attacks on hash functions and other cryptographic primitives. The impending arrival of practical quantum computers has spurred efforts to transition to quantum-resistant algorithms to secure data against future quantum threats. Post-quantum cryptography develops encryption algorithms secure against both classical and quantum computers. Lattice-based cryptography, code-based cryptography, multivariate polynomial cryptography, and hash-based signatures are leading candidates. These schemes rely on mathematical problems believed hard for quantum computers to solve. Governments and industry are standardizing post-quantum algorithms to prepare for the quantum threat. Transitioning cryptographic infrastructure is a massive undertaking requiring careful testing and deployment. Post-quantum cryptography ensures that sensitive information remains secure as quantum computing advances. Quantum clocks use atomic transitions to measure time with unprecedented precision. The frequency of light emitted or absorbed when an electron transitions between energy levels is extraordinarily stable, providing a natural tick. Optical lattice clocks trap atoms in lattices formed by laser light, isolating them from environmental perturbations. These clocks achieve accuracies better than 1 part in 10 to the 18, meaning they would lose less than a second over the age of the universe. Quantum clocks improve GPS, test fundamental physics like relativity, detect gravitational waves, and search for variations in fundamental constants. Quantum sensors exploit quantum properties to measure physical quantities with extreme sensitivity. Atomic magnetometers use quantum coherence of atoms to detect tiny magnetic fields, useful in brain imaging and mineral prospecting. Quantum gravimeters measure gravitational acceleration with precision, enabling underground mapping and earthquake monitoring. Quantum gyroscopes and accelerometers provide navigation without GPS. These sensors operate at or near fundamental limits set by quantum mechanics. As quantum technology matures, quantum sensors will transform medicine, geophysics, defense, and fundamental research. Researchers are exploring quantum positioning systems that could theoretically use entanglement to provide location information without relying on satellites. The concept involves distributing entangled particles to known locations and comparing measurements to determine position. If realized, such systems could offer improved accuracy, security, and resistance to jamming compared to conventional GPS. This technology remains in very early research stages with significant technical hurdles to overcome. The idea illustrates how quantum correlations might enable new capabilities, though practical quantum positioning systems do not yet exist outside of laboratory concepts. Quantum biology is an emerging field investigating whether quantum effects influence biological processes. Evidence suggests quantum coherence plays roles in photosynthesis, where energy transfer exhibits signatures of wave-like behavior that could help optimize efficiency. Some birds appear to navigate using quantum effects in specialized proteins sensitive to magnetic fields, involving electron spin states and radical pair mechanisms. Enzyme catalysis may involve quantum tunneling of protons or electrons, potentially accelerating certain reactions. The idea that olfaction, our sense of smell, might rely on quantum vibrations of molecules has been proposed but remains highly debated, with many researchers favoring classical explanations. Quantum biology challenges the assumption that warm, noisy biological environments always destroy quantum effects quickly. The field suggests that evolution may have found ways to exploit quantum phenomena, though much remains to be understood about where and how quantum mechanics matters for life. Some researchers have proposed that quantum processes might play a role in consciousness, though this remains one of the most speculative ideas in science. Roger Penrose and Stuart Hameroff suggested that structures called microtubules within neurons could support quantum computations, linking consciousness to quantum phenomena. However, the scientific consensus views this hypothesis with considerable skepticism. The brain operates at body temperature in a wet, noisy environment that would seem to destroy the delicate quantum states required. To date, no experimental evidence has demonstrated a connection between quantum mechanics and consciousness. While the proposal raises intriguing questions about the physical basis of mind, most neuroscientists explain consciousness through classical neural processes without invoking quantum effects. The transactional interpretation of quantum mechanics proposed by John Kramer pictures quantum events as involving handshakes between retarded and advanced waves, moving forward and backward in time. When a photon is emitted and later absorbed, the transaction involves waves traveling both directions, forming a complete event. This interpretation explains wave function collapse and avoids some conceptual difficulties of other interpretations. It provides a time-symmetric view where future measurements influence past emissions. Though not widely adopted, the transactional interpretation offers a unique perspective on quantum mechanics, emphasizing the interconnectedness of events across space-time. Relational quantum mechanics, developed by Carlo Rovelli, posits that quantum states are relative to observers. There is no absolute description of a system's state, only states relative to other systems. Measurements are physical interactions between systems, and the outcome is real only relative to the observer. Different observers may assign different states to the same system, and all descriptions are equally valid within their contexts. This interpretation eliminates the need for wave function collapse and treats all physical systems, including observers, on equal footing. It resonates with relational ideas in general relativity and offers a philosophically minimalist approach to quantum mechanics. Quantum Bayesianism, or cubism, treats quantum mechanics as a tool for agents to update their beliefs based on experience. Wave functions represent an observer's subjective knowledge, not objective reality. Probabilities in quantum mechanics are degrees of belief, analogous to Bayesian probability. Measurements are personal experiences that update the agent's beliefs. Cubism avoids paradoxes by rejecting the idea that quantum mechanics describes an observer-independent reality. Critics argue it makes quantum mechanics too subjective, but proponents contend it resolves interpretational puzzles by recognizing the role of agents. Cubism remains a provocative and influential interpretation. Quantum logic was developed to formalize the structure of propositions in quantum mechanics. Classical logic assumes propositions have definite truth values and obey distributivity. Quantum mechanics violates these assumptions because observables may not commute. Quantum logic replaces Boolean algebra with a non-distributive lattice structure, reflecting the complementarity and uncertainty of quantum observables. Though mathematically elegant, quantum logic has not supplanted classical logic in physics practice. It highlights deep differences between classical and quantum reasoning and raises questions about the relationship between logic and physical reality. Scientists envision a quantum internet as a network where quantum information could be transmitted, stored, and processed between distant nodes. Such a network would enable distributed quantum computing, allowing quantum processors at different locations to collaborate on computations. Quantum cryptography would ensure secure communication across the network. Quantum sensors linked through this infrastructure could potentially achieve unprecedented collective sensitivity. Significant challenges remain, including generating and maintaining entanglement over long distances, developing practical quantum repeaters, and interfacing different quantum systems. While small-scale quantum networks have been demonstrated in research settings, a global quantum internet remains a long-term goal. If realized, it would fundamentally transform communication, computation, and measurement capabilities. As you let these facts settle into your mind, allow yourself to drift. The universe is stranger and more beautiful than we can imagine. At the smallest scales, reality dances in ways that defy intuition. Particles become waves. Information cannot be copied. Observation shapes existence. These are not glitches, but fundamental truths, woven into the fabric of everything. The quantum realm is always there, beneath the surface of the ordinary, making possible the atoms that form your body, the light that reaches your eyes, and the neurons firing in your brain. You are a quantum system, impossibly complex, impossibly improbable, impossibly here. Let that thought carry you into restfulness. Let the mysteries remain mysteries, beautiful and calm. The quantum world does not demand answers, only wonder. Good night.